Welcome to this explainer, where we're going to tackle a fundamental, honestly pretty massive quantitative headache, pricing basket options when standard Black-Scholes math just completely breaks down. If you work in financial engineering, algorithmic pricing, or risk management, you know exactly what I'm talking about. Today, we're diving deep into a brilliant paper titled Beyond Log-Normal Sums by Dongdong Hu, Hassanjan Said, Steve Chonadek, and Frederick Viennes. We'll be thoroughly unpacking their exact probability representations, breaking down their four-moment approximation framework, and we are going to analyze every single piece of data and critical figure to prove exactly why their method works so incredibly well.
Okay, let's take a quick look at our agenda. 1. The basket option challenge. 2. A probability-first strategy. 3. Matching the four moments. 4. Evaluating standard baskets. 5. The crack spread proof. And finally, 6. Conquering the tail error.
Section 1. The basket option challenge.
So, to really frame the problem, we have to ask, why does the Black-Scholes model break down when pricing a basket of assets? We all know and love the classic Black-Scholes model for a single European option, right? It gives you a beautiful, clean, closed-form price. But what happens when you combine multiple assets? In the real world, your economic exposure almost never depends on just one single price. You're dealing with equity index baskets, complex currency portfolios, or energy spreads. And the moment you try to price an option on those combinations, that beautiful Black-Scholes math suddenly stops cooperating.
The root of the issue is that a weighted sum, or a difference, of correlated log-normal variables is not actually log-normal. When you have a basket option, you're dealing with a portfolio where some of the underlying assets might be weighted positively and others might be weighted negatively. Because of this, the resulting distribution of that entire basket is generally just unavailable in closed form, and your exercise region becomes highly nonlinear. Traditionally, to get around this, you'd have to fire up a Monte Carlo simulation. And sure, Monte Carlo is reliable, but it is exceptionally expensive computationally and painfully slow when you need to run it repeatedly across a whole surface of strikes and maturities.
Section 2. A probability-first strategy.
Rather than just trying to roughly approximate the payoff right at the start, the authors of our source paper take a really brilliant probability-first approach. Let's break down their methodology into three very manageable steps. Step 1 is a change of measure. They use Gaussian shift identities to rewrite the exact basket price as a linear combination of probabilities. Now keep in mind, this is purely exact math. There are absolutely no approximations happening yet. Step 2, for a standard basket, converts these probabilities into cumulative distribution function, or CDF values, of positive correlated log-normal sums. Again, exact. The brilliance here is how they are isolating the difficulty. The approximation only actually enters in step 3, where they replace each log-normal sum with a shifted log-normal variance mixture. This completely separates the structural, mathematical exactness of the pricing equation from the statistical approximation they use to solve it.
Section 3. Matching the four moments.
This is where the authors upgrade traditional distributional approximations, moving way beyond just finding the average and the variance. Unlike the classical Fenton-Wilkinson method, which just matches the first two moments, mean and variance, this novel probability framework matches four moments, the mean, variance, skewness, and kurtosis. The classical two-moment method usually just replaces the sum with a single log-normal variable. But think about it. Two moments cannot fully represent the highly skewed, heavy-tailed shape of a complex, real-world basket. So the authors introduce a shifted mixture, specifically a binary variance mixture. This gives the approximation enough flexibility to match all four of those crucial moments, while remarkably still retaining an explicit, easy-to-calculate cumulative distribution function. It's a huge upgrade.
Section 4. Evaluating standard baskets.
Let's actually dig into the data and thoroughly explain what we are looking at here, because this proves the empirical advantage of the framework. We are looking at standard baskets that have one positive weight and two negative weights. The bottom row is our true Monte Carlo benchmark. Now look at the top row, the direct three-moment approach. For basket 1, it spits out a price of 4.4766. Compare that to the Monte Carlo benchmark of 4.3738. That is a notable miss. But right in the middle, look at the probability four-moment row. It gives us 4.3740. It is virtually identical to the benchmark. And as you scan across the columns to basket 2 and basket 3, you see the exact same pattern holding up. The direct three-moment overshoots, while the probability four-moment method tracks the benchmark incredibly tightly. The exact probability reformulation combined with that critical fourth moment creates just a massive leap in pricing accuracy.
When you look at the aggregate results,
The crucial takeaway is that the mean absolute error drops to an incredibly low 0.0012 for the 4-moment method. That is tiny. Compare that to 0.0437 for the direct 3-moment approach. To really put that into perspective for you, the maximum absolute error for the old 3-moment method was roughly 0.10. For the new 4-moment probability method, it maxed out at just 0.0026. The authors rightly point out that this immense gain comes from two specific places. First, the exact probability reformulation does the heavy structural lifting, and second, adding that 4th moment to the approximation squeezes out all the remaining error.
Section 5. The crack spread proof.
Standard baskets are great for establishing a benchmark, but the real test is applying this to messy, empirical market data. Enter the 3-2-1 crack spread. This is a classic energy market trade that essentially models the profit margin of a refinery. You are long 2 units of Arbo gasoline, long 1 unit of ultra-low sulfur diesel, and short 3 units of WTI crude oil. Because this basket mixes positive and negative weights, its value can literally swing to either side of zero. It's the perfect proving ground. To handle this, the authors extend their framework to use a signed shifted log-normal proxy, where they actually assign a probability to the sign itself to ensure they can match those 4 complex empirical moments.
Let's thoroughly break down the baseline 1-year pricing data for this crack spread, calculated at a baseline strike of roughly $63. Down at the bottom, we have the Monte Carlo benchmark, which required 1 million simulation paths to arrive at a highly accurate true price of 14.8192. Now look at the 3 moments method at the top. It significantly overprices the option at 15.1945, which yields a pretty sizable absolute error of 0.3752. You really don't want to be off by that much on a spread trade. But check out the 4 moments method in the middle row. The analytical method absolutely nails it at 14.8775, shrinking that absolute error all the way down to a mere 0.0583.
By successfully matching that 4th moment, we see a staggering 84.5% reduction in absolute error at the baseline strike. I mean, 84.5%. That is a monumental improvement for an analytical formula that requires only a fraction of the computational power of a million-path Monte Carlo simulation. But to really grasp why this error shrinks so dramatically, we need to pop the hood and look at the underlying distributions.
Section 6. Conquering the tail error. This is where the paper's deep dive into cumulative distribution functions really shines. Let's trace how these metrics evolve over time. Look at the 30-day maturity row. The skewness is relatively low at 0.3548, and kurtosis is hovering near normal at 3.3073. Because the distribution is pretty well behaved here, both the 3-moment and 4-moment methods perform quite similarly in terms of root mean square error, or RMSE. But let's jump down to the 1-year mark. Wow, the skewness balloons to over 1.0, and kurtosis severely spikes to 6.3262. The basket's distribution has become heavily asymmetric and extremely fat-tailed. As a direct result, you can see the RMSE for the 3-moment method absolutely explodes to 0.2581, while the 4-moment method elegantly contains that error, keeping it down at 0.1723.
So, narrating exactly what we see in the visual density figures from the paper, the impact of time to maturity is crystal clear. At 30 days, a simple shifted log normal works totally fine. But at 1 year, that basket becomes heavily asymmetric. The absolute brilliance of the 4-moment density is that it perfectly tracks the true height and the specific shoulder of the Monte Carlo histogram. By capturing that exact shape, by forcing the approximation to match the true peak of this skewed distribution, the massive integrated tail error that typically plagues these models is vastly reduced. The exact mathematical identity from proposition 4.8 reveals a vital conceptual leap. It is the discrepancy in the exercise region, specifically the upper tail, that dictates your pricing errors. The paper proves mathematically that your option pricing error isn't about how pretty your curve looks or how well it fits the middle of the distribution. It is strictly bounded by the integral of the CDF difference only for the area above the strike price. Simply put, if your model doesn't tightly fit the specific tail region where the option actually pays out, matching the global moments won't save you.
And translating this mathematically proven concept visually, you can see that by conquering that tail error, the 4-moment method slashes the root mean square error by 1/3 at the 1-year maturity mark. The math definitively proves that if you control the discrepancy in the upper tail, you directly control and minimize your overall pricing error. And that is exactly why the 4-moment bar on this chart is so much lower.
Which brings us to our vital lesson for today. Option pricing is all about mastering the tail. You can match the mean perfectly, you can match the variance, you can even have the exact same skewness. But as Proposition 4.10 points out, positive and negative CDF discrepancies can cancel each other out over the whole real line, totally hiding massive structural errors in the specific tail region you care about. The 4-moment shifted variance mixture succeeds precisely because it has the inherent flexibility to mold itself to that highly asymmetric, heavy upper tail.
So, I leave you with this. How might this 4-moment probability framework revolutionize your own algorithmic pricing and risk management strategies? Because when you can price complex, mixed-sign baskets analytically, transparently, and highly accurately, without resorting to incredibly expensive Monte Carlo simulations, the possibilities are honestly endless. We've seen how restructuring the math to a probability-first format, and then rigorously applying a 4-moment signed proxy can tame even a wild empirical trade like the 3-2-1 crack spread. It slashes your computational overhead while simultaneously protecting you from tail risk pricing errors. Think about where you're currently burning valuable compute time on simulations and ask yourself, could a 4-moment proxy do it faster and just as accurately? Thank you so much for joining me on this deep dive. Keep exploring and keep questioning the math.